Dear colleagues, our next talk, our last talk in the evening session today is Iryna Kashuba from State University of Science and Technology. It's a big honor for me to present Professor Kashuba, who will tell us about semi-normal form for Sergeev superalgebra.
Thank you. Good evening. Can you hear me?
Yeah.
So I will try to share my file, right? Can see it, right? Okay. Once again, good evening. First, I would like to thank the organizers for invitation. It's a pleasure, always, and honor. And also, I would like to thank Armed Forces of Ukraine for letting this conference happen and also for keeping my parents safe. I'm going to talk about idempotence and basis which we construct using this for the Sergeev superalgebras. It's joined with Alexander Molev and Vera Serganova. Sergeev superalgebra is just superalgebra which can be constructed as a graded tensor product of two superalgebras, which is spin symmetric group. This is a version of symmetric group, but like you have the same relation, the usual relation for symmetric group, but TA, TB are they don't commute, they rather are anti-commutative if A minus B is greater than 1. And then you tensor it by Clifford superalgebra also, which is generated by C1, Cn, and here are the relations. There are also odd elements there. You also can have a presentation using the standard symmetric group, but then you lose tensor product and only have symmetric product. Sergeev superalgebras were introduced by Sergeev in 1985, and they are kind of parallel in, they play role of symmetric group in Schur-Weyl duality for super case. If you consider standard representation of Lie superalgebra Q, then both Sergeev superalgebra and this Lie superalgebra act on a tensor on nth power of this standard representation, and each algebra is a commutant of the other one. The more famous, probably than Sergeev superalgebra, is what is called Sergeev superalgebra admits affinization, which is called the generate-affine Hecke-Clifford algebra. Again, parallel to another even more famous, the generate-affine Hecke algebra. And you can consider basically both representation theories at the same time because you have a natural surjection from this affine Hecke-Clifford algebra to Sergeev superalgebra, and basically representation theory of Sergeev superalgebra can be deduced from representation theory of the generate-affine Hecke-Clifford algebra, superalgebra. Representations of Sergeev superalgebra were studied by Nazarov together with, as I mentioned, the generate Akha algebra, affine Hecke-Clifford algebra. It's semi-simple, and simple modules are parameterized by strict partitions of n, right? So it already was known, right? What we did, new one, is the following. So we, in his paper, Nazarov introduced Yutsus-Murphy elements inside of Sergeev superalgebra. They generate commutative subalgebra inside of Sn, and moreover, they act semi-simply on each simple module. So we would like to use those Yutsus-Murphy element to construct the complete set of primitive idempotence. It's semi-simple algebra, so it has to have set of primitive idempotence. Then using this primitive set of idempotence, we will construct what is called this is called for symmetric group algebra semi-normal basis. And also we use this basis to get explicit realization of all its simple module. And at the same time, we also get realization for all simple module for spin symmetric group. And finally, we would like to we gave a new version of fusion procedure for Sergeev superalgebra. it's a way to obtain the same primitive idempotence by evaluating certain rational function with values in Sergeyev superalgebra. This is all can be very nicely illustrated first by doing it for symmetric group, the result which is known already for 100 years, around 100 years or something. So I will start with it. So first, let's talk about Yutsov-Murphy elements for symmetric. Yeah, probably I'm a little bit like 100 years is too, but it's quite, at least for 50, 60 years it's around. Yutsov-Murphy elements, it's again, it's commutative, it's form commutative subalgebra inside of symmetric group algebra. This is actually sum of transpositions, right? They were used independently by Yutsov and Murphy to construct primitive idempotence for semi-simple group algebra, symmetric group algebra. For this, we use, so they are labeled by standard tableaus of shape lambda, right? So remember that what we have, like how one can classify representations by using standard tableaus, right? And here we're using the same, so we use this language of standard tableaus to construct idempotence. We do it by induction. We start with just identity element, and then we add, right? So basically, if you compare two tableaus, one is U and another is V, and you get V from U by removing a box occupied by N, then we have the following relation between this idempotence. So idempotence corresponding to U we can obtain by multiplying idempotent corresponding to V by this expression. What do we have here? We have here this Yutsov-Murphy element. These are the boxes, like the content of all edible boxes to shape mu. Right, and C is content of the box N which you removed when you get V box when you get standard tableau V from U. Then in that way constructed idempotence, you can see that more like Yutsov-Murphy elements act on them semi-simply, and with eigenvalue which is equal to the content of the box occupied by A. Moreover, those are primitive idempotents, they are pairwise orthogonal, and you can get a decomposition of group algebra just by summing up all possible shapes and all possible partitions for N, right? And in this way, you get a famous decomposition of group algebra into symmetric algebra into the squares of its representations. Right. What is semi-normal basis? What is semi-normal basis for symmetric group? We introduce intertwining elements. This is actually for any A from 1 to n minus 1. But then it's possible, here we have transposition, and here I use Yutsov-Murphy element. And it's possible to define it not for any A, but actually for any element of permutation group. And those elements will have the property that you can also, that you have, you can dualize it, right? And this correspondence, it will correspond to the element of inverse element of the group. Then we do the following. So if we consider a Young diagram of shape lambda, then for this shape lambda, we have also row tableau, which is done by just writing all elements. So you start with the first row from 1 till the length of this row. Then you continue in the second row. You just fill it from the top from the left to the right, and from the top to the bottom, right? So first row, second row, and of course it will be standard tableau as well. And it's easy to see that there is a unique permutation which takes any standard tableau to your row tableau of shape lambda. And finally, we introduce the following elements: zeta, Tu. So we have two standard tableaus of shape lambda, and we construct this element. This will be element inside of my symmetric group, right? Symmetric group algebra. When lambda runs over all Young diagram within boxes, those elements for each standard tableau, pairs of standard tableau tau and u of shape lambda form a basis for this group algebra. And you can see that it's just the following formula, the formula from the previous slide, now numerically, where f lambda is the number of standard tableaus of shape lambda. This is all just for symmetric group for the classical case, right? And this basis was used by Murphy to produce Young semi-normal form for simple as sigma n modules. We followed analogously for our for Sergeyev superalgebra. We'll do we did, and I will present it the same procedure. And finally, a fusion procedure for, again, we did it for Sergeyev algebra, but I will now talk about how it's done in classical case for symmetric group. It's another way to provide the same idempotence, complete set of idempotence, and it is called the fusion procedure. Again, it comes for symmetric groups from UTSUS. You take n variables and you consider rational function with values in this symmetric group algebra, very quite easily defined. You just take all product of, or in all lexicographical order for set of pairs AB. If I have tableau of standard tableau U, then I still put this as a content for box A. And Molev showed that consecutive evaluation, it's necessary to do it consecutively. You cannot put it, and I will show it with example, you cannot do it all at once. And the content is well defined, and it's again, you get idempotence also from this function. It's by certain scalar. Again, this is just a number of, it was defined here, right? The number of standard tableaus of shade lambda. So the idea is to do step by step all of this for the Sergeyev superalgebra. Okay, so first we have to introduce, they were introduced by Nazarov already, UTSUS Murphy elements for Sergeyev superalgebra. You see, instead of transposition, we have to introduce, this is generators, right? But like, you cannot just, so this is an analog of transposition of two elements, but in Sergeyev superalgebra, you define them by these generators of Sergeyev superalgebra, and then UTSUS Murphy element are given by these expressions. They pairwise commute. Next, again, Nazarov showed that irreducible representation of both Sergeyev superalgebra and spin symmetric group algebra are parameterized by strict partitions. The only difference with the usual case that you have to consider all the elements that each you have here strict inequality. Otherwise, everything is the same. It's still the length of partition, and the only one more difference that it's called shifted lambda tableau, that those elements are of they have some meaning. So that's actually, so this diagonal elements are important, and then so we have here shifted lambda tableau for this sequence, and diagonal entries are 1, 3, 7. Then again, it was shown that the dimension of simple Sergeyev module for this lambda, standard shifted lambda tableau is given by this formula here. G lambda is given by Schur formula, and here we have standard shifted, number of standard shifted lambda tableaus. And again, as in the previous case, you can define, you can get a Schur identity analogous to symmetric group algebra. Here we have, this is just, you still have the same, if you consider a spin symmetric group, you have the same equality here. Okay, so we do the same, well, it's like very analogous to symmetric group. The only thing that we have to consider shifted tableau and also bar tableaus. What are bar tableaus? It's just a shifted tableau. It's standard the same way, so you have to the numbers has to increase in each row and in each column. Here we have shifted, so it's like additional feature here. But also all elements on diagonal could be barred. Just we need, but only off diagonal elements could be barred, right? On diagonal, it could be only one. Only unbarred elements, right? So then again, we start computing this idempotence from identity for just one box. And again, we do it inductively and we compare just like U and V tableaus where you just, V is different from U that you took out box with N there, right? And by removing the box occupied by N, or in case you have N barred, occupied by N bar. Then we have to, content is actually almost the same. You have to switch it a little bit because it's sign content, so it has to have some sign. And but I'm not going to define it. It's not so important here. And still, it's actually the same formula. Here we have Yutsu's Murphy elements, and B are the sign contents of addable boxes. So it's like you suppose that you can add P boxes to V to obtain tableau with N elements, but you cannot add the same, you cannot add a box which will give you U. So this is how you describe all those addable boxes, addable P boxes, right? Then what we get are idempotents. They are orthogonal and they are full, so they give you identity, but they are not primitive. I mean, it's still not enough. We have more and we need, because here basically what we had is participation of this skew symmetric group algebra, right? It's the same formula here, and you have, this is a new letter for content, because as I said, like content is formula slightly changes if you have to consider barred and unbarred tableaus. So, for example, for n equal to 3, we have 6 bar tableaus. Again, remember, you cannot put, so here we have just one, so this diagonal, this element cannot be barred, so we have to bar both 2 and 3. And for this case, we only can bar 2. So that's why here we only have for this shape only 2 tableaus, standard tableaus, right? And then just using the previous formula, you can see, you can calculate those idempotents. So we have here this 6 idempotents corresponding to this 6 barred shifted tableaus. And you can check that they are really idempotents. To make them primitive, we have to refine it by elements of Clifford superalgebra. In super case, you have 2 conditions. So it's like you have two cases. So it's either this, here it's odd and even part, even and odd part, right? This is division of matrix. And here you have just matrix algebra. Again, I'm not going to define it. In any case, it's like both cases, both this algebras 2m and 2m plus indexed by 2m and 2m plus 1, they contain 2 to m primitive idempotents, which are corresponding to the diagonal matrix unit. They are pairwise orthogonal and form, again, the composition of identity of this Clifford algebra. What we do here, we have to choose certain idempotents from this Clifford algebra. So if you start again with barred standard tableau, then we have those diagonal elements, which are very important for Sergeyev superalgebra, as I said. So you choose the corresponding Clifford generators. And then you can again generate by these generators Clifford superalgebra, but just the smaller size, right? And then you consider inside of this one idempotence. And those idempotents which we will need to multiply. So you have the following with our, so now we define new idempotents, and this will be already the full set of primitive idempotents for Sergeev superalgebra. And this is just by multiplying all set of these idempotents with our idempotents which we got for skew-symmetric group. Then we have the following decomposition. Each left ideal Sn multiplied by this primitive idempotent is isomorphic to irreducible Sn module U lambda. So we got the first analogous theorem for symmetric, and in the same way we can, like, it's everything very analogous and follows very nicely, although like it's impression, if you compare, for example, these intervening elements with intervening elements for symmetric group algebra, they are definitely more complicated. This here, yeah, just so you have here both Clifford generators, and here is this actually transposition, and yeah, those are Eutsous-Murphy elements, right? You can do it for any element from 1 till n minus 1, right? But then also the same way we can, it can be generalized, it can be defined for any element of symmetric group, and we have. Again, we start with row tableau of shape lambda. We have now standard tableau, shifted standard tableau, shifted row tableau of shape lambda we are considering here. Still the same, we have unique permutation which make any standard tableau to, or rather to, which make our row tableau to any standard tableau. Remember that we use two tableaus, right, to define those basis element. And here we have something more added. We need to add something more. We need to take a subset of non-diagonal boxes and allow them to be barred. So basically, we have lambda given for shifted Young diagram of shape lambda given. We have two standard shifted tableau, and we still have a subset of boxes which of diagonal, which we will bar. So if we now take our row tableau and denote it lambda beta by adding to all elements, all boxes in beta, in subset beta, by adding those bar, then we define these elements. These are elements in Sergeev superalgebra. Here are idempotents corresponding to this idempotents we constructed, which correspond to this row tableau, which depends on beta now, right? And here we multiplied by intervening elements corresponding to those elements which takes t to which takes rho to t and u to t again, right? So this expression, so we have this labeled by two partitions and set of subset of non-diagonal boxes. So, and all these elements associated with a pair of standard unbarred tableaus of shape lambda and set beta of non-diagonal boxes form a basis of the Sergeev superalgebra Sn, which is called semi-normal form, basis and semi-normal form of Sn. As a result, we also, as a consequence, we also get explicit realization for simple modules, and not only for our Sergeev superalgebra, but also for simple modules over spin-symmetric group algebra. Here. Finally, fusion procedure. Again, we follow symmetric group case, right? It was not introduced this small phi AB, right? Let me just, I don't think it's, yeah. Yeah, so you see, it was just product of all expressions like this. Very simple. We have to do it a little bit. So just instead, not only this, but yeah, here, right? So we have this impression. It's a little bit different, but if you write it in a presentation using symmetric group, you have this first part, which is like exactly the case of symmetric group, but then you have to add this Clifford generators to make it and change sign here. So it's kind of generalization of what we had for symmetric group. And then again, you have lexical, you take product on over all pairs taken in lexicographical order. It will be big function, huge rational function with values in Sergeyev superalgebra. And if we take shifted tableau, and we take standard BART lambda tableau, we have shifted diagram, and we take standard tableau of shape lambda. Then for every A, we put this is content, signed content again for entry A. And it's the entry of U. So if we do consecutive evaluation of this big function, rational function in those contents, consecutive is important here, we again get our idempotents which correspond to those which correspond to standard BART lambda tableau, not primitive, but those the big one which correspond to sign to skew symmetric group. So so we would like to explore more, because there are ways to there are applications to like Capelli identity, like immanence, which were constructed by Kunikov for symmetric groups. So we would like to do it, to do something, to continue to explore this for Sergeyev superalgebra. And also, because we have Sur-Sergeyev duality, we actually can use this information to get something new in representation theory of queer superalgebra Qn. And yeah, we can do again, continue this analogy. There are a lot of certain things application are already done for symmetric group, and we believe that it can be repeated for Sergeyev superalgebra, and also we can use it for representation theory of queer Lie superalgebra as well. So I will use last 2 minutes just by showing the example. It's just the same tableau we considered in the first example when I constructed idempotence. This is how this rational function looks like. You cannot directly evaluate it in all values which are content, content, right? So you see that you cannot substitute use all U1 and U3 equal to 0. It will kill this guy, right? But it's easy to see that with certain transfer, of course, they are easy to calculate here relatively, right? You can do deduct it to have this expression, and you can obtain the corresponding idempotent, and if you compare it with my first example, it will coincide. So basically, we have that both. It's illustrated our theorem on this example, and I finish with this. Thank you very much.